Welcome to this presentation on the fundamentals of reservoir fluid behavior, a field guide for engineers. This guide, prepared by Petroleum Engineer Mohamed Salah, is designed to help you master the essential principles for classifying oil and gas reservoirs. As Tariq Ahmed notes in the Reservoir Engineering Handbook, naturally occurring hydrocarbon systems are complex mixtures that exhibit multiphase behavior over wide ranges of pressures and temperatures. As a petroleum engineer, your primary task is to study, characterize, and predict the behavior of these fluids. The fundamental questions are not merely academic. They are economic. Is the accumulation an oil or a gas reservoir? How will the fluid's phase state change as pressure and temperature decline during depletion? And, crucially, what is the optimal development and production strategy to maximize the net present value of the asset? Fluid classification, based on the initial reservoir conditions and fluid composition, is the absolute critical first step in strategic reservoir management. Three critical points anchor the PT diagram. The critical point, C, is the unique condition where the properties of the liquid and gas phases become identical, and the bubble point and dew point curves meet. The Cricondentherm, TCT, is the maximum temperature on the phase envelope, above which the mixture can only exist as a single-phase gas, regardless of pressure. The corresponding pressure is the Cricondentherm pressure. Finally, the Cricondenbar, PCB, is the maximum pressure on the phase envelope, above which the mixture can only exist as a single-phase liquid regardless of temperature. These points define the thermodynamic limits of the hydrocarbon system and are fundamental to the classification process. The initial and most fundamental diagnostic step is the critical temperature test. This involves comparing the constant reservoir temperature, T, to the fluid's critical temperature, Tc. This comparison establishes the primary classification as either an oil or a gas reservoir. If the reservoir temperature, T, is less than the critical temperature, Tc, the reservoir is classified as an oil reservoir. This is because the reservoir temperature line intersects the phase envelope on the left side, meaning the initial reservoir pressure, pi, is on the bubble point curve or to the left of it, placing the fluid initially in the liquid or two-phase region. This is the path for black oils, volatile oils, and low-shrinkage oils. For oil reservoirs, the subclassification is determined by the relationship between the initial reservoir pressure, pi, and the bubble point pressure, Pb. An undersaturated oil reservoir is characterized by pi being greater than Pb. The fluid is initially a single-phase liquid, and production can occur without gas liberation until the pressure drops to the bubble point. A saturated oil reservoir has pi equal to Pb, meaning the oil is already saturated with gas, and any pressure drop will immediately cause gas to evolve, forming a secondary gas cap or dissolved gas drive. A gas cap reservoir has pi less than Pb, indicating that the reservoir already exists as a two-phase system with a free gas cap in equilibrium with the oil phase. This distinction is vital for determining the primary drive mechanism and calculating the initial oil in place. The spectrum of crude oils is a continuum, primarily categorized by the gas-oil ratio, or GOR, and the oil shrinkage factor. Low shrinkage oil, or black oil, is heavy, dark, and has a low GOR, typically less than 200 standard cubic feet per stock tank barrel. As the GOR increases and the oil becomes lighter, we move through ordinary black oil to volatile or high shrinkage oil, where the GOR can exceed 3,200 standard cubic feet per stock tank barrel. Finally, near critical oil is characterized by a critical temperature very close to the reservoir temperature, resulting in extreme shrinkage and complex phase behavior that borders on gas condensate behavior. The choice of production equipment and the accuracy of material balance calculations are highly dependent on correctly identifying where the reservoir fluid falls on this spectrum. If the reservoir temperature, T, is greater than the critical temperature, Tc, the reservoir is classified as a gas reservoir. This means the reservoir temperature line intersects the phase envelope on the right side, or not at all, placing the fluid in the gas phase region. The subsequent subclassification of gas reservoirs is determined by the reservoir temperature's location relative to the phase envelope and, specifically, the Cricondentherm TCT. This comparison is crucial because it dictates whether the fluid will exhibit retrograde condensation behavior or remain a single-phase gas throughout the reservoir's life. Gas reservoirs are subclassified into three zones based on the reservoir temperature, T, relative to the Cricondentherm, TCT. Retrograde gas condensate occurs when T is between Tc and TCT. As pressure drops, the fluid enters the two-phase region, causing liquid to condense, the counterintuitive retrograde behavior. Wet gas is found when T is greater than TCT, but the fluid's dew point curve is still close enough to the reservoir temperature that liquid condenses at the surface separators. Finally, dry gas is characterized by a reservoir temperature well above TCT, and the fluid remains a single-phase gas in both the reservoir and its standard surface conditions, with only water condensing at the surface. This classification is vital for predicting liquid recovery and designing surface facilities. The behavior of retrograde gas is a critical challenge in reservoir engineering. The initial state is a single-phase gas above the dew point pressure. As the reservoir is depleted, the pressure drops isothermally, and the fluid crosses the dew point curve, causing liquid to condense in the reservoir. This is known as liquid dropout. The liquid volume increases until the pressure reaches the maximum liquid dropout point. This condensed liquid, often a valuable hydrocarbon, can block pore throats, leading to a significant and often irreversible reduction in gas permeability and well productivity. Further pressure reduction causes the fluid to cross the dew point curve again, and the condensed liquid begins to revaporize, eventually returning to a single-phase gas at very low pressure. Understanding and mitigating this liquid dropout is essential for maximizing recovery from these reservoirs. The phase behavior we observe is a direct consequence of the fluid's molecular composition. The composition is typically broken down into light components, primarily methane and nitrogen, intermediate components, C2 through C6, and the heavy components, C7+. The triangular diagram visually represents this compositional connection. Fluids rich in light components tend toward the dry gas classification, while fluids rich in heavy components, C7+, tend toward the oil classification. A key rule of thumb is that fluids with more than 12.5 mol% of C7+ components are almost always liquids or oils in the reservoir. This compositional analysis is the bridge between laboratory PVT data and the macroscopic phase behavior seen on the PT diagram. For accurate reservoir modeling, particularly with equations of state, the heavy, undefined C7+ fraction must be properly characterized. This is a significant problem because all components heavier than hexane are lumped together. To model this fraction, we must estimate its critical properties: critical temperature, critical pressure, and eccentric factor. We achieve this by using established empirical correlations, such as the Riazzi-Daubert and Edmister correlations. These correlations allow us to calculate the necessary critical properties from two easily measured values: the molecular weight and the specific gravity of the C7+ fraction. This characterization process is essential for tuning the equation of state to accurately predict the phase behavior of the reservoir fluid. Applying the C7 plus characterization process involves a two-step calculation. Given the measured molecular weight and specific gravity of the C7 plus fraction, Step 1 uses the Ricci-Daubert correlation to estimate the critical temperature, critical pressure, and critical volume. This correlation is a powerful tool for predicting the thermodynamic properties of the heavy fraction. Step 2 then uses the Edmister correlation, which is a function of the critical properties, to calculate the acentric factor omega. The resulting calculated properties, such as the acentric factor of 0.5067 in this example, are then used as the pseudo-component properties in the equation of state model, enabling accurate simulation of the reservoir's fluid behavior. This flow chart provides a complete, systematic diagnostic workflow. The process begins with the initial reservoir pressure and temperature. The first critical decision is the critical temperature test. If the reservoir temperature is below the critical temperature, we follow the oil path, which involves comparing the initial pressure to the bubble point pressure to classify the oil as undersaturated, saturated, or gas cap. If the reservoir temperature is above the critical temperature, we follow the gas path, comparing the reservoir temperature to the Cricondenthorm to classify the gas as retrograde, wet, or dry. After the initial classification, a confirmation step is vital, using secondary clues like gas-oil ratio, API gravity, and the fluid's compositional ternary diagram. The final output is a confident fluid classification and behavior prediction, which is the essential foundation for all reservoir simulation and development planning. Thank you for your attention. This presentation, which provided a deep dive into the fundamentals of reservoir fluid behavior, was prepared by Mohamed Salah, a fresh graduate petroleum engineer from Cairo University. I am eager to apply my knowledge of petroleum engineering to real-world challenges and contribute to the industry. Please feel free to connect with me using the contact information provided on the slide for any further discussion or opportunities.